said, hey, you, let's do some DiffEQ. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some DiffEQ. Today, we're going to find solutions to first-order differential equations that require a technique that you're likely already going to know. The equations that we'll look at are of this form. dy over dx is equal to f of x. It's worth noting that f of x depends on the independent variable x only, and there is no presence of the dependent variable y. Though we'll look at first-order differential equations, the technique that we use can be applied to second and third order so long as they are of this form, as the technique that we'll use can be applied repeatedly. But let's look at the method that we'll use to solve such differential equations. Given that we have a function dy over dx is equal to f of x, if we think about what this means intuitively, it's simply saying that we have a function y such that if we take its derivative, we get f of x. This is simply saying that y should be the antiderivative of f of x. And that's really all there is to it. This is a technique, anti-differentiation, that you would have seen in calculus too. Now let's look at our first example. So here's our first example. We have dy over dx is equal to cosine of x. From what we saw with our method, it should simply be that the solution is y is equal to the antiderivative of cosine of x. If we do the anti-differentiation, we get the following. As a chance to get some practice, let's check that what we found is the solution to this differential equation. So here we have our solution, and if we simply take the derivative of both sides, what we get here is exactly the same as our initial differential equation. That shows that this is indeed the general solution. Let's look at another example. Here we have the function dy over dx is equal to x times e to the x squared. We know from our method that if we want to find the solution, it is simply equal to the antiderivative of the right-hand side. So here's our solution in its integral form, but we'd like to actually compute the antiderivative if possible, and we can do that in this case. We can use a technique that we would have seen in calculus 2 called u substitution. For u substitution, we'll pick our u to be x squared. Now, like any case of u substitution, if you pick the wrong u and do the substitution, you'll see that you haven't eliminated every instance of x, and you know you need to pick a different u. But trust us in this case that x squared is the proper choice for u. Taking the differential of both sides gives us the following, and then doing a little bit of algebraic rearrangement gives us this equation. Now if we substitute back into this expression, what we get is the following. Now since we're integrating in terms of u, and we simply have e to the u, the antiderivative is going to be easy to compute. Notice since we're taking an antiderivative, or doing an indefinite integral, we end up with the parameter plus c. Now it's worth noting that when you have a first-order differential equation, you should end up with one parameter. If you had a second-order differential equation, you would end up with two parameters. A third-order differential equation, three parameters, and so on. We want to do one last thing. We want to back substitute. And now having back substituted, we have our expression y is equal to a function of x, and because it is a first-order differential equation, we have one parameter. This is the general solution here to this differential equation. Let's look at another example. Here we have a differential equation paired with some initial value information here. So this is an initial value problem. When we're talking about just the equation with one or more derivatives, we're talking about the differential equation, but when we add this initial value information, it becomes an initial value problem. Now this is not in exactly the form that we'd like it to be as far as the differential equation portion, but with a little bit of algebraic rearranging, we have this equation here. Now we know from our method that if we want to find the solution, it's going to be the antiderivative. And if we go ahead and compute the antiderivative, we end up with the following. And now, as far as the differential equation goes, we found our general solution. However, since we have initial value information, we can compute this parameter. When you have just a differential equation of nth order, you'll end up with a general solution containing n parameters. If you have enough initial value information, you can solve for all your parameters. The number of pieces of initial value information that you need is equal to the order. So if we have first order differential equation, we want a single piece of initial value information. So let's go ahead and substitute that into our general solution to solve for our parameter c. Here we substituted x being pi over 4 and y being 2 per the initial value information. And if we do some further computations, we get that c is equal to 3. This tells us that the solution with the initial value information is negative tangent of x plus 3. Now here we have the general solution if we had just this differential equation, and then we have the exact solution that we can obtain once we have an initial value problem. Now let's consider our last example. Surprise! This differential equation is not written in the form where we have applied our method so far. However, by rewriting it, we can get it into the form that we would like. Let's rewrite it. For the first step, notice I'll multiply by dx as if it was a algebraic or numerical quantity. Then I'll divide by dy in the same way. Finally, I'll divide by y to the fourth, alternatively multiplying by y to the negative fourth. Now notice, this has the general form of what we have written before, but you may be confused by the fact that the variables are switched. Before, what we had was a differential equation where the dependent variable was y and the independent variable was x. The independent variable was x, and we had a function of just x. Now what we have is what looks like a switch in the variables, with x being the dependent variable and y being the independent variable. And over here, it's a function of y, but this is actually a form that we like and can apply our method to because the independent variable is y and the function over here only depends on y. Now let's go ahead and apply our method where we have changed which of the variables are independent and dependent. Here I've rewritten the equation. Here we've solved for the dependent variable, which is now x. We compute the antiderivative and find that it's negative 1/3 y to the negative third, remembering that we need to have our parameter since we're taking an antiderivative. And now we should note that what we were originally trying to find in our differential equation was a solution y equals some function of x. Here we have the case where y is taken in the negative 1/3 power. So we want to do some algebraic manipulation so that we isolate y if we can. It's not always possible, but it will be in this case. I've multiplied both sides of the equation by negative 3. Notice that the parameter c becomes c1. That's because I did multiply c by negative 3, and I've simply relabeled that as c1. That is, negative 3c is equal to c1. Now we'll continue to isolate for y. We move the c1 to the other side. We do some cross multiplication, and then we take the cube root of both sides. Now what this initial value information says is that x is equal to 0 at the same time y is equal to 2. If we substitute that information into this expression, what we get is that 2 is equal to this expression, and we find that c1 is equal to negative 1/8. This gives us a final exact solution of the following. It's worth noting now that once we have an exact solution and there are no parameters, we can specify the domain of that function. So for instance, the only place this function won't be defined is when the denominator is equal to 0. That means that negative 3x plus 1/8 should not be equal to 0. And if we do some algebra, we'll find out that x should not be equal to 1/24. Looking back over the rest of the work we did, we find out there's no other place that would cause there to be a breakdown in the relationship between x and y. The only place where we have potential undefinedness is at this point. So the domain for this particular solution is everywhere except when x is 1/24. Well, I hope you found this video helpful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.